I'm Peter Hill and welcome to practice science lessons in my garden, and I'm going to give a talk today about neutrons. I've got my little model of a neutron here, which is in actual fact a ping pong ball. It's actually not a very good model. So let's talk about neutrons. You can't go down to the local shop and buy a bottle of neutrons, and people in a health food shop can't sort of give you a bottle of neutrons for healthiness. The reason is that neutrons are little particles. They're like hydrogen, except and protons, but they're in fact they're neutrons, and they're actually unstable. So this little guy will hang around for 14 minutes and 39 seconds, around a quarter of an hour before it goes bing and explodes back out to a hydrogen atom. So let's talk a little bit about a neutron. A neutron is a fundamental particle. That is, it's sort of the base particle of nature. It's different from an elementary particle. Like an elementary particle is like an electron, a lepton, a neutrino, a quark. They're elementary, in fact, that they're so small they have no explanation for their internal properties. But neutrons do have a few working parts, so they're fundamental but not elementary. So back in, it sort of began before 1932, a guy called Chadwick discovered the neutron. So let's go back a bit of a story. Before it, people were seeing these unusual events. They were firing an alpha particle at beryllium, and the alpha particle, which is a helium nucleus, which we'll talk a bit later. This has been coming out of some radium or alpha particle sources that people were able to find naturally around the place, and they'd put beryllium foil in front of them, and this beryllium foil would explode and create paths ahead, and invisible paths, or things that would be as if there was an invisible neutron, because it was not creating a track or anything like that. And so let's talk about a charged particle and a track first off. So charged particles, if this is charged and it moves through the air really quickly, it drags electrons and bangs things. It's very large, it's charged, it's moving too quickly, and it causes the air to ionize, and the air ionizes, and when you get a sudden chill in the air and a cloud begins to form, it will form first around this little tube of ionized particles. So they could see that there was an unionized particle coming out of the beryllium and knocking off particles. It was sort of like snookering. Now, the person who was onto this was Marie Curie's daughter. She was seeing this, and her mum, Marie Curie, said, "Look, you're mad," and dissuaded her. And this left the discovery to Chadwick. Now Chadwick, there's a little bit of a story about Chadwick. He was what we would call spectrumy. So the legend is that he got lost in Cambridge and wanted to do accounting, but turned out up to go into the physics course instead, and was too shy to say he didn't want to do physics. So that led him to do physics, and his basic style led him to discover the neutron, because the neutron would go through, and he said it had to be the same mass because it was knocking off individual protons out of, I think it was paraffin. So if you can imagine if you have, say, a cherry tree, and individual cherries magically fall off, you say, I think it's been shot with a BB gun rather than with a bazooka. So that's his general discovery. So we have the neutron here, and it's the sort of magic ingredient which makes nuclei stable. So in fact, there's generally about, I think it's a power law more, there's substantially, say, 235, uranium-235, which is very famous. 235 refers to the total amount of let me see, baryons. These are neutrons and protons are called baryons. Neutrons, protons, and something called mesons, which are slightly smaller. They're a little momentary sort of particle made out of a quark and antiquark come together. They're called, let me see, hadrons. So they're hadrons. Baryons are these that come out here. So your nucleus has to have these guys in it. In fact, this is what happens, that if I produce one of these, and these get produced all around me at the moment, if I had a neutron detector, that would be going off about 1 second. Occasionally when a cosmic ray comes in, that cosmic ray does a splatteron and produces heaps of neutrons. If there's some lightning going around, the acceleration causes a bit of nuclear implosion. If there's fusions, there's lots of neutrons. If of course I have a uranium reactor, the neutrons are coming out all the time. So the neutron, now we'll do a little bit of physics about it. The neutron has two fates. It can be a free neutron like this, and 14 minutes and 39 seconds away will suddenly explode. When I say that, it's 50% of them. So they'll be exploding all the time, and if I have a box of them, if I have a box of 100, and I give them as a birthday present to you, and you sing happy birthday for a while and have a bit of party games, you come in and you go, what? It says 100 neutrons in here, there's only 50. And of course if you waited a full hour, there'd be a half, a quarter, an eighth, 16th, and so you get really rather disappointed. So if you get a box of neutrons, know that they're going to decay, so open them up quickly so you can enjoy them. But the other thing that a neutron can do is it can go like this, and because it hasn't got a charge, it can actually move through an atom, and we'll talk about that in a little sense. It can actually go straight into the nucleus and stick and build up a nucleus, and so half the actual neutrons, the neutrons that you do have, will stick to nucleuses, and often when they do, they produce a little X-ray. This is an important thing. Now, one of the things that we want to point out is that neutrons are not like this ball here. In fact, I'm going to watch it here. I can actually do this one. Watch this ball, and it went straight through my hand. See, it's a bit of. In fact, I'll tell you what actually it is. I actually pass it behind my hand, but it could actually go through my hand. And if you hold your hand out and you dropped your neutron onto it, the neutron would sail right through. So neutrons can actually pass right through matter because it doesn't have a charge. It doesn't feel the it doesn't feel the electromagnetic force. So it is actually a wave. So if I drop a neutron, I will drop it all the way through. If I dropped it here, it would go right through my head, right through my body, through the ground, until it actually, say, hit a water body beneath me, and then it would hit water. So there's one thing that neutrons tend to grab onto. So let's go. When neutrons slow down, it's rather sad, because they are waves, as they slow down they get bigger and bigger, their cross section gets bigger and bigger. So a very fast neutron goes really quick. It's if you like, it's a long cigar shaped thing, so you don't know exactly where it is, but its actual cross section is small. As it gets larger, it becomes bigger and flatter. That's a wave, because it's a quantum wave, as you describe it by quantum wave. And in fact, we should go into the quantum wave aspect of it. So, hello to my friends at ANSTO. They're not really my friends. I try and talk to them, but they always get really upset when I start talking quantum physics to them. So what I was going to say is that a nucleus is not as it's drawn. The nucleus that you see with a whole lot of these little guys bunched in and a whole lot of protons bunched in is not really accurate. I don't know if you've ever noticed, it's rather spooky about how these nucleuses look as though someone's got a bad flash player and they move around, they never rotate, and they look very two-dimensional. They may be made three-dimensional, but they never rotate or do anything like that. And they have a feature which is unlike what these guys are really like. They're made so they are actual ping pong balls, and you can actually stick them together with glue, and I don't know, it goes like that. And the fact is that people don't talk about them being wave-like properties, and they say they've got hard surfaces. But a neutron is a quantum particle, and as a quantum particle it doesn't have a surface, it doesn't have an inside or outside. There's no surface, and so there's no inside or outside. You can actually just pass through a neutron. And for instance, in a nucleus, the actual electrons pervade the entire atom, including the nucleus. It all goes through there, or sit on top of each other as waves. And so this, say if I have here a proton and I have a neutron, and I stick the two together, the two slows down, goes up big, sticks together. When it sticks together, it forms heavy water, it releases a X-ray, so I can actually see, I can measure those X-rays and see where water is if I drop a neutron onto a water source. And what you have at ANSTO or in your physics textbooks is separate, but what in actual fact happens, it slides through as a quantum wave, sits on top of it and produces a deuterium particle. So a deuterium particle is fundamental. So so it's not two separate things. The actual neutron is actually a wave inside the proton, or the proton's a wave inside it, so it forms a nucleus. Now, this is one of the things that's happening, is that as your neutrons go in, they build up. They just keep on sticking inside the nucleuses, and when there's fundamentally too many neutrons, it says I'm no longer stable, and it converts into a proton, and you get this is it transmutation of the atomic periodic table. So if I get a periodic table and I fire neutrons at that periodic table, those elements will get heavier and then turn into protons and actually move across. And that's actually how the periodic table filled up. And this is a neutron source hitting ordinary matter. So you have first instance is neutrons produced in the Big Bang produced helium, and more about half the mass of the universe is now helium. So I've got one helium of 4 and three protons left. So originally I started off with 7 protons. 2 of those turned into neutrons to make a helium. This is the first few minutes after the Big Bang, and then I've got 3 protons. So it's 1 to 3. There's 1 helium to 3 protons, but you know, half the mass is helium. We nearly cooked off. Now, what's happening in our star is that we get 4 protons. They go together to make a helium, converted into neutrons. The proton gets fused with, you could say a proton gets fused with a helium, or captures not a helium, captures an electron, turns into a neutron, and releases energy as it does so, and produces the inside of stars. But this process continues on, and sort of in stars you get a series of the triple alpha process to what is it? NOC, it's CNO cycle, carbon cycle. You've got cycles in stars which produce heavy matter, but as the matter has been produced, it produces large fluxes of neutrons, and so you have basically a neutron reactor, and you have a slow neutron source which produces some of the periodic table. You have a fast neutron source in a big bang. So late sequence stars have millions of years, so they produce an element, and basically by the time they get back to add it under the model, that's sort of like the lazy tradesmen. They come along, they fix up your door 1 week, they fix up your roof 1 week, and they walk away for another year, and your house keeps on falling down. They never quite build your house. So you've got your slow neutron source and your fast neutron source. These paint the periodic table. And then there's these mystery things where there's just huge amounts of heavy elements and you don't know where they come from. And they think, oh, they now know it's from neutron stars. How do they see it coming on? Well, because nowadays the future has arrived and we have gravitational wave telescopes around the Earth, 3 around the Earth, and we can see a explosion, a stellar cataclysm. This is 2 neutron stars coming together. We can pick it up. You know, listen. Oh, that sounds like a neutron star. Where does it goes? It's somewhere out there, and all the telescopes in the world, with hooked by optical fibers and into space telescopes, all train in the area, and they pick up this area, and they can watch. The gravitational wave, I think, comes a little bit faster than the light waves. I don't know quite how that happens, but it takes, I could well imagine, various processes for that. And so they can actually watch a neutron star come, neutrons come in, and gold comes out, and so they could see the production of gold by these fantastic stuff. So you can actually make gold, and of course, the property of nuclear bombs and nuclear reactors is that I have some uranium in a tube here. I've got uranium in this tube, this side, and a neutron and concrete metal between this side. The neutron can go out of here, it comes out of here quickly, gets slowed down by something called a moderator. It slows it down, comes out to this side, slows down, hits onto a uranium, it goes like that, and separates into 2. But then again, I must warn you against the Bohr liquid drop model, which has neutrons and protons being heavy, sort of like balls with a surface on them. They can't go together. Of course, they've got no surfaces. They actually slide through each other, and your nucleus is a full-on quantum mechanical device. I want to say a little bit about neutrons. So they don't have a charge, but they do have a magnetic field, i.e. that if I had a neutron here and I wanted to pick it up, I could actually pick it up with a magnet. Well, it's not attracted to a magnetic field, it's attracted to a magnetic field gradient. And that is, if your magnets do not detect magnetic field, they detect magnetic field gradients, because you've got a dipole, and so you're comparing your north pole to your south pole. The north pole is more attracted than your south pole is pulled away, so you've got a gradient there. But I find that these guys have a magnetic field generated from them, and it says that there is charge circling inside. Now, charge circles inside from fundamental particles called quarks. So when you say fundamental, you can no longer use physical models, you can only use mathematical models as a thing. But it looks the same inside the neutron, that there's an equal amount of positive and negative charge. There's a positive 2/3 of a charge for an up quark and 2 down quarks. And it looks naively as though the down quarks are on the outside and the up quark is on the inside. And so when it's spinning, it's got a net charge, a net greater current of electricity. So you make a battery, sorry, not a battery, a magnet, simply by this. It is the amount of current going in a circle, like this, like that, and the area. So the amount of current going in a wire determines the magnetic field at any point, and the area gives you that magnetic field times the area. It's the I times A. So there is actually a current coming up here, but as they've worked this out, they've said that this must have other particles inside, and they have found that the neutron inside has 3 quarks and gluons. So gluons are sort of the equivalent to sort of light in not in the electromagnetic field, in a strong force, and they've got a thing called unlike that, they actually have I suppose energy and charge in it. It's actually, so if you can imagine light was charged, you could steer light around with an electric charge. So you could actually make, in theory, a gluon ball with no quarks whatsoever. There are 3 quarks in the centre, and so this little baby here has got inside 3 quarks. The important thing is that I'm holding this model here. This has got no, a real neutron has no inside or outside, and the quarks don't exist in our dimensions. They exist in strong force dimensions, and the gluons. So it's got this property going on, but there's actually no spatial extent in our universe for it to go on. So you can get one of these guys, and you can actually fire, if you could, fire an electron into it, and it would go out in squirts. So it would blow out, and its inner guts would come out, and the gluons would form streams, and the streams form particles coming out. So that's how we know that there's gluons here. Now I want to talk about something called so it's got a magnetic moment, and so related to, it's something called angular momentum. So angular momentum is spin, what we call it for these particles, which are called fermions. They have a strength of half a Planck's constant, it's h bar on 2. Depends whether you use frequency, angular frequency, or just normal everyday frequency, whether you use h on 2. But let's talk about that for a moment. What they talk about, there's these things that they talk about. It's got a measured angular momentum of h on 2. The actual quarks have them in, and they add up. There's got an odd number of quarks to form in a fermion. I wish I could describe this a little bit more. But the actual quark, so it's got a spin of a half. It's got a projection of plus or minus a half. But it's actually got, and it's got a spin quantum number of a half. But the spin, angular momentum spin, has got actual length a little bit longer than a half, because it's got to go out there and have a projection of a half or minus a half at this angle. And so its length is the square root of a half into 1 plus a half. So it's the square root of 3 on 4, or the square root of 3 on 2, if you can follow that. So the actual length of the angular momentum vector is slightly longer, and it's got its projection, and as it goes round it precesses such that it's only got a projection there. So this is one of the things that you have to really pick in. They tend to gloss over when they're going through, in terms of that it's got a quantum number of a half, it's got a projection of a half, but its length, half is just a naming convention for the actual length, slightly different. And so it actually possesses it, the angular momentum, it's, if you like, it's spinning, but it can't actually spin. And the reason is that why do physicists get upset when you talk about a proton or a neutron spinning like that? Why do we have it upset? We get upset because if it was spin with sufficient to get the value of angular momentum that we wanted to, and had any appreciable size, it would be actually spinning faster than the speed of light, and also would see other effects due to spin. So it's, when we say spin, we say quantum mechanical spin. It's from a fundamental aspect of it. It's got the property of angular momentum, but none of the mechanics. That's what we mean for it. So we've covered this, and that the neutron can travel. It also means that the neutron can travel through things, and it's a little magnet. And in fact, it would be fantastic if I had a little magnet and I could fire it through things. I could see all the little magnetic fields inside, and they come across, and because it's a wave, because neutrons are not particles, they're a wave, they can form a beautiful picture outside. So a neutron, if I go through here, if I go through it here, it comes out like here. But if it's a wave, it forms a beautiful curvy pattern on the sides. That is, that if the whole is equal to the wavelength of it, it starts to diffract, and it will diffract on the outside. And this is the entire aspect in terms of that people's entry into the world is they don't want to learn anything more, but it is far more complex than that. And we have a beautiful tool called the neutron. Now, I feel I should do a party trick or like that type of stuff. Thanks a lot for watching, and this has been a practice lesson on neutrons.